So today I will be talking about designer van der Waals materials for new photonic and new phononic properties. So first, let me briefly introduce my lab. My lab is called the SCOPE lab. SCOPE stands for Sensing, Characterization, and Optoelectronics. So in our lab, we have a lot of fun making designer quantum materials, including 2D materials and topological quantum materials. We made these materials for mainly two purposes. We first want to generate new optical and electronic properties, and we also want to develop new biosensing paradigms. When we make these designer van der Waals materials or quantum materials, we basically are creating new types of materials. So we also want to obtain quick and relatively accurate understanding of the material's properties. So we are also developing machine learning accelerated characterization for these materials. So regarding van der Waals materials, there are actually lots of materials. They cover almost the entire electromagnetic spectral range. For example, in the far infrared range, we have graphene. It has zero band gap, and its plasmonics is in the terahertz range. So it's very useful for far infrared and terahertz applications. At the other end of the electromagnetic spectrum, we have UV light, and here hexagonal boron nitride is very useful. It is an insulator. It has a very large band gap in the UV range. In between, we also have the family of transition metal dichalcogenide, or TMD materials. And many of these materials have a visible band gap. And in the electromagnetic spectral range, we have an important range called mid-infrared. And here, there are several 2D materials, including black phosphorus, and several emerging materials that can be useful for these applications. So for these van der Waals materials, we think the most exciting aspect of these materials is it's relatively easy to make designer van der Waals materials. So you can make some artificial structures out of these van der Waals materials and approach their properties to what you desire. So for example, we can make these heterostacks and homostacks of van der Waals materials. We can make this so-called Janus monolayer, where you replace an entire subatomic layer of atoms by another type of atoms. So you have this asymmetry introduced in these layered materials. You can also introduce atomic doping, atomic defects in the materials relatively easily with relatively good control. And you can also change the material shapes. For example, you can roll them up, and these have all proved to be efficient ways to tune these material properties. So for the first part of my talk today, I want to first talk about this atomic doping, atomic defects, and show you how we generate some new optical emission, in particular single photon emission. So single photons are photons emitted one at a time. And these single photons have affirmed our understanding of quantum theory, stimulated applications, and have been recognized by the 2022 Nobel Prize in Physics. So these flying qubits play a crucial role in encoding, transmitting, and transducing quantum information. They basically form the foundation for many approaches of quantum communication, quantum computing, quantum sensing, and metrology. So regarding single photons, for different applications, we have different requirements for them. So for example, we want the single photon emitted have certain purity. They need to be bright enough, and they need to be indistinguishable. And the emitters that emit these single photons need to be reliable. Of course, we also want them to have low decoherence. For certain applications, we may have different requirements. For example, spin-photon coupling, room temperature operation for the single photon emitter, and the emitter photons to be in the telecom band for especially communication applications. So to generate these single photons, we need to create these single photon emitters. And one way to create this is to introduce atomic defects in the solids. So for the correct type of atomic defects, they can have this two-level system in the band gap. And for a single defect like this, they can emit single photons. So a very famous example for this is nitrogen vacancy center in diamond, or NV center in diamond. So in 2D materials, they can also be host materials for single photons. So if you create atomic defects in these 2D materials, they can also emit single photons. And these host materials include hexagonal boron nitride, tungsten diselenide, indium selenide, tungsten disulfide, and so on. So these are just very few examples of a vast number of works, and many researchers have contributed significantly to this field, including theoretically and experimentally. So there are several advantages of using 2D materials as single photon emitters, including the relatively precise control of the defects, because you just need to manipulate in the 2D plane rather than the 3D material. And they have a relatively good or easy photon extraction, because the photons just are extracted from the 2D plane. And they are also ready to integrate with photonic structures. They're easy for fabrication purpose. So actually, single photon emitters in 2D materials have already been integrated in cavities, waveguides for on-chip integration. They are also very useful for fundamental understanding, for example, cavity QED. On the other hand, there are also challenges. So for example, the purity and indistinguishability of single photons emitted from 2D materials still need to be consistently and significantly improved. In addition, deterministic generation of single photons from these 2D materials as well as 3D materials need to be improved. So for the first part of today's talk, I want to show you two of our recent works on how we tackle some of these challenges. The first example I want to share with you is a single photon emitter in boron nitride. And the defect here is carbon doping, or a carbon defect. We introduced this carbon defect by in situ synthesis. So we introduce carbon when we synthesize boron nitride. And as a result, we have a thin film of boron nitride with a thickness about 30 nanometer. And in these boron nitride thin film, we have carbon defects in it. So first, we want to understand the depth distribution of the carbon dopant. So we use a technique called TOF-SIMS, time-of-flight secondary ion mass spectrometry. So you can see the carbon distribution on the depth profile looks like this. So they're relatively uniformly distributed across the entire depth of the sample. Now, if you look at the chemical bonding environment of these carbon defects, you can see from the XPX spectrum, the carbon is bonded with both boron and nitrogen. And if you look at the Raman spectrum, you can see the Raman modes of boron nitride is slightly redshifted and widened compared to the pristine sample. So these are all proofs that carbon has been effectively integrated in the boron nitride lattice. So next, let's look at the optical emission property. So eventually, we want to look for single photon emitters for these materials. So actually, at room temperature, if we measure the photoluminescence spectrum, we can see some very sharp and bright peaks coming out. So these apparently are from the carbon defects, because pristine boron nitride has a very large band gap in the UV range. In addition, we realize these emissions are polarized in plane. So that means there is an in-plane dipole moment for these emitters. So we have these bright emissions. We want to confirm if these are single photon emitters. So experimentally, to confirm the single photon nature is to use this HBT interferometry, or Hambry-Brown twist interferometry. So we have a 50-50 beam splitter, which separates the beam into two identical optical paths. Each ends with a SPAD, or a single photon avalanche diode. Then you can calculate the correlation between the signals detected by the two SPADs. So you can have a G2 function. The G2 is a function of the time delay between the two SPADs. So now you can imagine, if we only have a single photon entering this HBT interferometer, it can only go through one of the optical paths. So the G2 at 0 time delay should be 0. So this is called an anti-bunching feature, and it's a feature for single photon emission. Now, if we look at the carbon defects in our boron nitride, we send these emitted light to the HBT interferometer, and this is our experimental results. So you can see apparently G2 at 0 time delay is very, very small. It is as small as 0.015. And this actually translates into a high single photon purity, 98.5%. So the purity is basically 1 minus the G2 at 0 time delay. So this 98.5% of single photon purity is actually one of the highest among single photons in boron nitride at room temperature. So why do we care about a high purity for single photon emission? So basically, the purity is required for almost all quantum applications. For example, if you want to do quantum key distribution, you want at least 99.5% of single photon purity. If you want to do boson sampling, generating GHD states, you want 98% of single photon purity. And for other applications, you have different requirements for single photon purity. So for our sample, we get 98.5%. So it already meets the requirements for several quantum applications. So not only do we have a high single photon purity, but these emitters are also very bright and highly stable. We characterize the brightness of our emitter to be almost 500,000 counts per second. In addition, if you continuously excite the emitter for over 5 minutes, you do not see any blinking, and you do not see any wandering of the emission wavelengths. So this signifies the high stability of these single photon emitters. In addition, we realize our emitters have high Debye water factor. So a Debye water factor describes the percentage of photons emitted into the zero phonon line rather than the phonon sideband. So high Debye water factor is very important for achieving high brightness of single photon emitters. So now if you look at the photoluminescence spectrum, you can see there's a sharp peak. There are also some shoulders and some small peaks over here. So the sharp peak corresponds to the zero phonon line. And these small peaks correspond to the phonon sideband and also second order phonon sideband. You can also see there's a small shoulder here corresponding to the LA phonon of boron nitride. So now if we calculate the area under each of the peaks, we realize our Debye water factor, the area, the percentage area under the ZPL is about 45%. So this is actually a pretty high value for single photon emitters in boron nitride at room temperature. Now if we compare this to several other single photon emitters in boron nitride, reported in literature, you can see their phonon sideband is quite comparable with the zero phonon line, indicating a much smaller Debye water factor. So our Debye water factor is much better. Now this 45% of Debye water factor for our sample is still very decent, even if we compare to some other very famous single photon emitters. For example, dye vacancy in silicon carbide, G center in silicon, and NV center in diamond. You can see these values are not very high, and some of them are even at low temperature. Of course, there are also other single photon emitters with high Debye water factor. For example, the silicon vacancy center in diamond. So there's still room to improve for single photon emitters in boron nitride. In addition, we realize our emitters have the Schelling states. So if we measure this G2, this second order autocorrelation function, with a long delay time, we realize there's a bunching feature. So this bunching feature indicates there are some very slow decay process. And you actually have 2 additional decay lifetimes, about 30 microseconds and 3 milliseconds. Now, this slow decay lifetime indicates there's metastable states involved in the defect emission. Now, if we compare these lifetimes to the radiative decay lifetime, which is about 5 nanoseconds, we realize these tau2 and tau3, the slow decay, is about 6,000 to 600,000 times slower than the radiative decay. And this signifies a dominant radiative relaxation process, meaning highly efficient single photon emitters. So overall, if we compare our emitters with other single photon emitters in boron nitride, we can see indeed we have a very good single photon purity, very large brightness, and so on. So this is very exciting. We get a high performance single photon emitter. Now, if you look at this table more carefully, our sample is carbon defects in boron nitride. And some of these other works are also carbon defects in boron nitride. So this makes us wonder, why is our sample better? We're all carbon defects. So with that question, we collaborated with theorists from Oak Ridge National Lab, and we looked at a number of defects in boron nitride. So these include monomers, for example, this single carbon substitution, antisides, and vacancies, as well as dimers, which is a combination of these monomers, as well as trimers. And in particular, we're looking at this so-called CBC and CNC. So CBC is carbon substituting boron, nitrogen, boron sequentially. And CNC is carbon substituting boron, nitrogen, boron, nitrogen sequentially. And we also looked at these tetramers as well as the donor acceptor pair, or DAP. So this DAP is carbon substituting boron and nitrogen, but they're not adjacent to each other. I should also mention there is a comprehensive calculation done in monolayer boron nitride, and you can refer to this work. For our work, we looked at bulk boron nitride because our sample is about 30 nanometers thick. So we have many candidates. We need to first screen them. So the first step to screen them is to look at the optical absorption spectra of all of these defects. So if these defects have optical absorption close to the experimental value, and if they are polarized, we think they are valid candidates. So after looking at all the defects candidates, we have 7 left. So you can see in all these cases, there is optical absorption close to the experiment, and they are all polarized. So we still need to screen them. There are still 7 candidates. So the next step is to look at the thermodynamic stability. So we looked at the formation energy of these defects. So these are the formation energy calculated for a number of defects. You can see there are several defects with very low formation energy. However, they are not in these optical lists. So these should be excluded. So after analyzing all the defects, we realized these are possible defects. They're the DAP and the trimers, including CBC and CNC. Okay, so then we need to check more closely for the DAP and CBC and CNC. So we looked at the Gibbs free energy at different synthesis temperature. So here I'm plotting the Gibbs free energy difference for 2 types of defects at different synthesis temperature. So this plot means if the Gibbs free energy difference is positive, dimer is preferred. Otherwise, DAP is preferred. The black curve is the actual calculated value. So you can see these are all positive. That means dimer is more preferred than DAP. And in other words, in this synthesis temperature, DAP is not stable. So that means DAP should be excluded in our list. So our candidates left now are CBC and CNC, the trimers. So if we look at CBC and CNC, you can see their Gibbs free energy difference is very small, actually. So that means most likely both of them coexist in our sample. However, depending on the actual synthesis temperature, one of them may be more dominant than the other one. So this is our synthesis temperature. We can see our temperature is relatively low, so CBC should be more dominant in our sample than CNC. Now, if you look at other works, so these are the synthesis temperature for other works. You can see they use a relatively high synthesis temperature, and the CNC should be more dominant in their samples rather than CBC. So this is probably the main difference between our sample and other samples. In our sample, we have CBC dominant, and in other samples, they have CNC dominant. And the main difference here is the synthesis temperature. And this is because we use a method called pulse laser deposition. It can still achieve a relatively good crystal quality with a relatively low synthesis temperature. Okay, so we know CBC is dominant in our sample, and CNC is dominant in other samples. Now the question is, CBC and CNC, which one is a better emitter? So to answer that question, we used a more precise calculation method called GWBSE. So here we are still looking at the optical emission spectrum. This is CBC, this is CNC. You can see apparently CBC has a brighter emitter close to the experimental energy. So CBC is a better emitter, and it lines better with our experiment. We can further look at some metrics. So here we can see these values for CBC matches very well with our experiment. So this further confirms our sample is CBC dominant. So basically, CBC is a better emitter than CNC, and it's dominant in our sample, making our sample a better single photon emitter. So actually, after we submitted our work, we found another work posted on arXiv, and they actually confirmed the experimental observation of the CBC defect. So this gives us more confidence that we actually have CBC in our sample. All right, so this is the story about single photon emitters in boron nitride. Now, let me switch gear a little bit and talk about another host material for single photon emitter, which is transition metal dichalcogenide, or TMD. So for single photon emitters in TMD, a conventional issue is still the low single photon purity. So this is a normal single photon emitter in tungsten diselenide, a type of TMD that you can expect. So this G2 here is about 0.4. This translates into a single photon purity about 60%. So apparently it's not enough for a number of applications. Now, if you look at the photoluminescence spectrum, you can see there's a very sharp peak that corresponds to single photon emitter, but is sitting on this large background. And this is actually commonly seen in literature. So if you look at these other literature, you can see the single photon emitter peak always sits on this large background. And this large background actually compromises the single photon purity. The reason we see such a large background is when you try to excite single photons in these tungsten diselenide, you inevitably excite many other processes, such as the other defect levels, dark states, tryons, and so on. So these many processes constitute a large and continuous background. And your single photon process is only one of these many processes. It shows up as a sharp peak, but it's sitting on this large background. So to further improve the single photon purity, we need to suppress this classical background. So we developed several strategies to do so. The first strategy is to select polarization. So we know for monolayer tungsten diselenide, there is a K and K prime values. They correspond to different circular polarizations of light. So now you can imagine if we use co-circular polarization for excitation and detection, meaning you use the same polarization for excitation and detection, you inevitably excite this band-to-band transition. So this will constitute a large classical background. But now if we use the cross-circular polarization, meaning a different circular polarization for excitation and detection, this limited valley hopping will effectively suppress the classical background. And potentially you can improve your single photon purity. So this is our experiment. You can see the blue curve is cross polarization. It has a much smaller background, and the single photon purity is much better. So the G2 is much lower. Single photon purity is much better. So this actually corresponds to 98.3% of single photon purity. We further looked at several other spots in the sample. So for all of these spots, you can see the cross polarization gives you a much better single photon purity. Now, if we summarize the G2 we measured for all of these spots, you can see there are several G2 that have very small value. All of these correspond to the cross polarization case. Now, if we look at the first principles calculations, we can find the evidence. So here we consider a single defect or vacancy in tungsten diselenide monolayer. You can see these K and K prime values are indeed strongly spin split. But you can also see these flat bands that correspond to the defect bands. They are actually spin degenerate. And this means they can host excited electrons with arbitrary spin. So no matter what kind of circular polarization you have, the defect emission intensity is not affected. But the band-to-band transition intensity is affected. And this is why we can improve the single photon purity. All right, since now we're using the valley dichroism to achieve better single photon purity, And we now know, we also know the valley dichroism depends on the excitation wavelengths. So can we further manipulate the excitation wavelengths to improve the single photon purity? So with that in mind, we carried out an experiment with different excitation wavelengths, 520 nanometer, which is off resonance, and 718 nanometer, which is near resonance. So these are the results. So you can see for off resonance, from non-polarized to cross-polarized, the single photon purity is improved by 61%. But now if you look at the near resonance, from non-polarized to cross-polarized, the single photon purity is improved by 75%. So this is much better. But additionally, if you pay attention to this value, so this G2 is only 0.01. And this corresponds to an even higher single photon purity of 99%. And this is actually a record high value for single photon purity in tungsten diselenide. All right, so this is very exciting. We can achieve a high single photon purity by controlling the light polarization. But for a number of applications, you may not want to use your light polarization just to improve the single photon purity, because the polarization can be useful for other purposes. For example, to detect chiralities of molecules. So can we still achieve high purity single photons without controlling the light polarization? Well, the answer is yes, and it's actually very simple. So instead of using monolayer, we can look at bilayer tungsten diselenide. Because for bilayer tungsten diselenide, it no longer has a direct band gap. So bilayer actually has an indirect band gap. And also because of the inversion symmetry for bilayer, the K and K prime values are no longer spin split. So let's look at our experimental results. So this is a bilayer PL or photoluminescence spectrum. This is a monolayer. You can see the single photon emission. Here, the intensity is not compromised compared to monolayer, and the background is also suppressed. And as a result, we can have a G2 of 0.03, which corresponds to a high single photon purity of 97%. So now if we look at the first principles calculations, again, this K and K prime values are here, but you can see they are no longer spin split, and this is forced by inversion symmetry. And we can also see these flat bands that correspond to the defects, and they are actually doubly degenerate with effective zero spin density. So they can also host excited electrons with arbitrary spin. So overall, if we summarize the G2 measured for monolayer and bilayer, we can see for bilayer, you can relatively easily achieve lower G2. And for most of these results, they're without polarization control. So yeah, so we can still achieve high purity single photons without controlling the light polarization. And the solution, a simple solution here is just to use bilayers. In addition, if we summarize the G2 as a function of the peak to background ratio, we can see with a relatively high peak to background ratio, you can easily achieve a lower G2 or high single photon purity. So suppressing the background is an effective approach to achieve high single photon purity. So I also need to mention there have been other efforts to improve single photon purity. For example, people try to use the charge transfer molecule to suppress the classical background. You can see in this work, they use this type of molecule and put it on top of tungsten diselenide. The sharp peaks from the emission will show up, and these are actually single photon emitter. But without these molecules, they cannot see single photon emitters. In addition, you can use electrical bias to deplete some charges from tungsten diselenide. So you can see in this work, if they apply this electrical bias, they can suppress the G2 very effectively, achieving better single photon purity. So compared to these methods, our methods are actually very simple. You can control the light polarization, or you can just simply work on a bilayer. So our methods do not need extra efforts on the design, fabrication, and material engineering. So if we summarize our results, and in comparison with other results for tungsten diselenide and other TMDs, and you can see indeed we have a very good single photon purity of 99%. But I also want to emphasize that our methods can consistently achieve high single photon purity. So we do not just achieve one good single photon purity with some fortunate discovery. Our method can consistently achieve high single photon purity. So for example, among all the spots we measured using chirality control or bilayer, 90% of the spots we measured are single photon emitters, meaning G2 is below 0.5. And 28% of all the spots we measured have high single photon purity over 90%. So this is actually a very high percentage. In contrast, if we don't use any of the purity control methods, if you just look for single photons on your sample, among all the spots we measured, only 29% of them are single photon emitters, and none of them are of high purity, over 90%. So basically, this method is very consistent. It helps you to achieve good single photon purity. But also, our methods, because of the simplicity, it can be easily combined with existing techniques. For example, the molecule, charge transfer molecule, or electrical bias method. It can further improve the single photon purity for other samples. So this is the story I want to share with you about single photon emitter. So let me now switch gear a little bit and talk about phonons, and in particular, phonon interference. So this is a very interesting phenomenon that we discovered recently, and we are looking at a very special sample called a 2D metal. So the way we have these 2D metal or 2D atomic layers of metal is like this. You start with a material called silicon carbide, and then you heat up the silicon carbide. So carbon will sublime and to form very thin layers of graphene on the surface of silicon carbide. So this is a well-known technique to generate or to fabricate graphene. It's called epitaxial graphene. So simply by heating up this silicon carbide. And then this graphene layer on top of silicon carbide is not perfect. It has defects, it has cracks. So now if you evaporate metals onto this structure, you can actually have some of these metals will penetrate the graphene cracks or defects. They will form 2D atomic layers of metals between graphene and a silicon carbide. So in particular, in our case, we are looking at the metal silver. So we have 2D silver between graphene and silicon carbide. We have a strong evidence here. If you look at the cross-sectional TEM image, you can see this is silicon carbide. These are graphene, but in between, you have 2D atomic layers of silver. So now we have a very unique structure, 2D silver. It's different than the normal silver atomic structure. What's interesting about them? Well, we measured the phonon modes in these samples, and we found something very interesting. So for example, if you just look at silicon carbide and the phonon modes in this spectral range, there's nothing particular. You have some small modes. These correspond to the normal silicon carbide Raman modes. Now for graphene on silicon carbide, still very similar, nothing in particular. But you can see as long as we introduce this 2D silver, you have these modes strongly enhanced. And not only that, these modes do not have this conventional Raman mode shape or phonon mode shape, right? The conventional Raman modes have the symmetric Lorentzian line shape. But these apparently are not symmetric. So they have the shape called Fano line shape. So the Fano line shape is a result of the interference between a discrete state and a continuum state. The discrete state is basically the phonon modes. The continuum state can be several reasons. They can be electron excitation, they can be defected phonons or phonon polaritons, and so on. So because of this interference, we have this Fano line shape. You can see from this equation, there is a parameter called 1/q. So 1/q describes how asymmetric this line shape is. You can see if 1/q goes down to 0, this is just the normal Lorentzian line shape. The larger the 1/q, the absolute value of 1/q is, the more asymmetric this line shape is. All right, so basically we have seen the Fano line shape for these 2D silver. Now, if we actually look closer on these samples, we can see different phono patterns on these samples. So in this spectral range, we have several modes of silicon carbide. They are called folded longitudinal optical mode, or FLO mode. There are several FLO modes, FLO 2, 3, 4, 5. There are 4 modes in this range. We can see in some areas, we can see this FLO 2, 4 patterns. So these are phono line shape, they are enhanced, they are activated actually. In some other areas, we can see this FLO 2, 5 modes. So these 2 modes are activated. And in some other areas, we can see this FLO 3, 4 modes. Why do we see different phono patterns? Well, if we look at the spatial distribution, we have some clues. So for example, if you look at the optical image of this 2D silver surface, you can see these stripped structures. These are actually due to the different terraces of silicon carbide. So we know the silicon carbide, in our case, is 6H silicon carbide. They can have different surface terminations. And this gives you these structures of terraces. Now, if we map this structure and the phono patterns, we realize the FLO 24 and FLO 25 actually show up alternatively. So apparently, these phono patterns are dependent on the surface termination. In addition, if we just look at one terrace, we can actually see FLO 3,4 and 2,4 coexist. So apparently, this also depends on some fine structures or the defects in particular in those terraces. So basically, we know the formation of different phono patterns depends on the surface termination of silicon carbide and also the specific defect structures in these silicon carbide surface. But now if you look at this 1/q values, as I mentioned, the larger the 1/q, the more asymmetric the line shape is. And that means a stronger interference, phonon interference, between the discrete state and the continuum state. So here we actually have a 1/q very large. The absolute value is about 30. If you compare this with other phonon modes observed in other materials, you realize this 1/q factor is at least an order of magnitude higher than any other materials. So this is very exciting. We have a very strong phonon interference or quantum interference in these phonon modes. So what's useful about these large quantum interference? Well, for one thing, they can be useful for sensing. So here, we demonstrated the single molecule sensing using these phono modes. So here we use a model molecule called rhodamine 60. We deposited different concentrations of these molecules onto the 2D silver surface. You can see with the increase of concentrations, the phono mode have some changes. The intensity increases, the line shape is a little different. In the bottom, we have the pristine sample and solvent only. So pristine means nothing is done onto the 2D silver, and solvent only means just water, no molecule. All right, so now if we summarize the intensity of these modes and 1/q factors, we can see they change monotonically with the molecule concentration. And in particular, for this 10 to the minus 12 molar, this corresponds to a single molecule under the optical beam. So that means we can detect a single rhodamine 60 molecule. Not only that, we can see compared to the pristine sample, there's already a significant change for the mode intensity and also in particular this 1/q factor. So actually we have seen 43% of change of mode intensity and 78% of change of 1/q factor with just a single rhodamine 60 molecule. So this is actually a very sensitive probe to detect this single molecule. Well, why do we detect these single molecules? For rhodamine 60, their optical resonance is actually aligned with the optical resonance for 2D silver. So this triggers an energy transfer between the 2D silver and the molecule. And the molecule fluorescence actually altered the phonon interference in these 2D silver, causing the sensing of these molecules. So because of this, right, so we can see rhodamine 60 has optical resonance aligned with 2D silver. This causes a big change to the phono mode. If for some other molecules, their optical resonance is detuned from the 2D silver, you can imagine a smaller change to the final mode. So with this, we can actually achieve some level of selectivity for molecule sensing. So for example, this is the optical absorption spectrum for 2D silver. You can see rhodamine 6G actually aligns with the peak. There are some other molecules like PDCDA that also aligns with the peak. There are other molecules like CuPC, F16 CuPC that are detuned from this optical resonance. So if we actually look at the final mode intensity, we can see this aligns. The intensity aligns with how detuned these molecules are with the 2D silver. So with this, we can achieve some selectivity for molecule sensing. So with this, let me just stop here, acknowledge the collaborators involved in the works I've described. Our students and postdocs who actually performed the work, our funding support, and thank you for your attention. I'm happy to answer questions.